still like finishing up. Like I'm trying to secure type of person before I start looking at the because I think I got 19 at the homework. No, I just missed the last problem and I was doing like the hand problems. I did 5 of them. And then I totally forgot to do it. It was like some really hard problems and like that was
Yeah, I'm not reading chapter 16, 17 on that whole complex.
I'm trying to catch up with the and I'm doing the one where I'm doing it like
all right, it's 1 o'clock. Hope you all had a good weekend. I'll remind you that if you have any questions on the take-home, feel free to come by and talk to me. I'm encouraging you to do that. In fact, I wish I could insist that you come by and talk to me because I really think that most of the understanding happens when you're able to talk through something with someone. But like I said before, I can't force you to come to my office. So that take-home is due, what, a week from today? Okay. If you're doing it, right? If you're going to do it. I'll explain how these work after class if you want. All right, so now we are going to pick up where we left off, and we're a little bit behind. All right, so I'm going to have to kind of try and speed us up a little bit to get us where we need to be without sacrificing blowing your brains up. All right, so let's see how this goes. Last time we were talking about vector functions and space curves. So we said we can define a vector function r of t to be either 2-dimensional or 3-dimensional, and that each of the components can be functions of t, and that when we start letting t roll through different values, we're going to draw things in either 2 or 3-dimensional space. And we had done, the last example we did was this intersection of 2 cylinders. And I said we'd come back and we'd talk about the domain, but I just don't have time for the domain, so I'm just going to move on, and I think we'll be okay without it. But I want to show us some other vector functions that are just cool to look at if we used a computer to graph them. So here's a what we call a toroidal spiral. And this is, if you've ever seen or heard of what's called a torus, it's basically a donut. Okay, so this is a curve, a path around the donut. So you can see it kind of spirals around the donut. It's called a toroidal spiral. And that is an example of a vector function. All right, 3-dimensional, right? Creates this pretty cool picture. And the vector function is hard to see here, but remember it has 3 components, right? Each component function, the x, y, and z. Here's what they are. I use r instead of t here, just so you know. But it's 4 plus sine of 20t times cosine t. That's your first component function. Your second component function is 4 plus sine 2t times sine t, and then your last component function is just cosine 20t. If you were to graph that, plug in different values of t, you would get that. Okay, kind of a cool shape, cool path through space. Here's another one called a trefoil knot or trefoil knot, and kind of hard to see it, but basically ties a knot. Okay, so it ties a knot upon itself. So you start letting t roll, and you start drawing all these vectors, and you draw the knot. Okay, so that's another one. So that's just kind of illustrating how it's nice to have technology to be able to get an idea of what these things look like, right? What some of these space curves can look like. We talked last time about the limit of a vector function, right? And the limit of a vector function was real nice because all you did was take the limit of each of the components. Well, the derivative, great news, is the same exact way. If we have a vector function either in 2 or 3-dimensional space, and we want to know the derivative of the vector function with respect to t, then all we have to do is take the derivative of each component function individually. Very nice. Now, you're going to do them individually. Within each one, yes, you might have product rule, you might have chain rule, quotient rule, all the rules will apply, but you just do them separately. And the important thing is that the answer that you get when you take the derivative of a vector function is that you get a new vector function. Okay, so your answer is actually a new vector function. Just like in Cal 1, when you took the derivative of x squared, you got 2x, a new function. When you take derivative of a vector function, you get a new vector function. So here's the geometric meaning, okay? We know that in Cal 1, if you have a function, the derivative somehow is related to the slope of the tangent line. Well, with a vector function, we have something similar. So if we're given a value of t, then the value of the derivative of the vector function at t is a vector, which is tangent to the curve at the point r of t. So here's an example. Whoa, hold on. Yeah, let's work through a mechanical example first, then we'll take a look at the picture. So real quick, let's find the derivative of this vector function. So r prime of t here, we have to take the derivative of this two-dimensional. This is a two-dimensional vector function, right? So this draws a curve in two-dimensional space. So if I take its derivative, I take derivative of these separately. And to take the derivative of t sine t, then, bless you, what am I going to use there for that? Product rule, right? So you take derivative of t, which is 1, times sine t. So I get sine t plus derivative of sine t, which is cosine t, right? Times t, so t cosine t, comma. And now the other one is very similar, right? But we're going to get cosine t, what? Minus t sine t. Sorry, I'm trying to cram all that in there. So just two quick little product rules there, right? So now that we've taken the derivative, let's find the vector which is tangent to this curve at pi over 2. So let's plug pi over 2 into our derivative for t and see what we get. So what's r prime of pi over 2? So it's a vector, right? Sine of pi over 2? 1, right? Cosine of pi over 2? 0. So that zeroes out. So we just get 1 here, comma. Cosine of pi over 2 is 0, and then sine of pi over 2 is 1, but then times pi over 2. So negative pi over 2? Y'all with me or not? Okay. So that is a vector in two-dimensional space, isn't it? So if I were to graph that vector in two-dimensional space, if I start at the origin, I'd go out 1, and then negative pi over 2. Negative pi over 2 is what? Like approximately 1 point something? Yeah, so it's probably going to be like, I don't know, close, whatever. Close, like that. This vector should be tangent to our curve, right? But remember, vectors can move around. So let's take a look geometrically at what we've got. All right, so here's the curve, all right? That blue curve is the actual original vector function. This is, what's the vector function? T sine t? Yeah, this is t sine t, t cosine t. It actually draws like a spiral. It goes like this. It goes like that when you draw it. It's not really that relevant right now, but what we've done is we've said, okay, let's go to pi over 2. So if we plug pi over 2 into the function, pi over 2, let me just plug it in. Pi over 2, that's where we are. Okay, so the black, this is a black arrow, that black vector is the original vector function, right? It's telling us where to point onto the curve. So that's r of pi over 2. But then the red vector is this vector, okay, which I drew over here, but now we've moved it. We've moved it from here over so that it starts out where this point is on the curve. And you notice that that curve appears to be tangent, doesn't it? that vector, sorry, appears to be tangent to the curve. Yes?
So does the magnitude of r prime of t have anything to do with
Absolutely.
Okay.
The magnitude of that vector is going to matter. In fact, let's move around right now and notice, of course, as we move through time, notice that the vector changes direction, right? But isn't it also changing its length? Does it appear to be changing its length? It looks like it got smaller that way. It looks like it's getting longer here, doesn't it? And that length is going to have, well, it's going to have some sort of geometric meaning. But, you know, we can imagine it's kind of like the tangent line, but it's a vector, not a line. And so, yes, we have more than just direction now. We have the length of the vector itself. All right, so let's go ahead and talk about a couple of other things related to it. First, what's called the unit tangent vector. So if we take, remember that if you ever have a vector and you want to find a vector that points in the same direction but has a unit length, that's called a unit vector. All you have to do is take the vector and scale it by 1 over its own length. We did this a while back. So this idea of a unit tangent vector says, okay, great. If you take the derivative of a vector function, you're going to get a vector. If we want to take that vector, maintain its direction, but just make it have a length of 1, then all we have to do is divide it by its own length. And when we do that, we get what's called the unit tangent vector. And we will see in this following picture the unit tangent vector. So this is the same picture we just had. The red vector is the derivative of the vector function, right? It's changing length. But the unit tangent vector, capital T of t, is always pointed in the same direction as the red, but notice its length never changes, right? And that we'll use later when we do flux. We're going to want unit tangent vectors instead, because all we care about is direction. So we don't care about length. All right, so we just needed to make sure we have a formula for calculating that. All right, so, you know, find this. Well, we just did this, right, didn't we? This capital T of t would be r prime of t over the magnitude of r prime of t. That's the formula. And so if we wanted to know capital T of pi over 2, we would be taking the derivative at pi over 2 and dividing it by its own length. And what was the derivative again, the vector? It was 1 negative pi over 2. 1 comma negative pi over 2. We take that vector and we divide it by its own length. And, oh, I don't need that. What's the length of that vector? It's kind of weird, but what is it? Square root of these things squared and added up?
I got 3.5.
You got 3, is that after the square root or before?
That is before.
Before the square root, so 3.5 in here? Everyone understand all we're doing is 1 squared plus negative pi over 2 squared? Adding them up and then square rooting? So essentially what you're going to have is a vector. It's going to be that divided by, and then what's square root of 3.5? 1.86. And then the other one, which is kind of weird, negative pi over 2 divided by 1.86. We're going to have decimals, but it's just, again, showing you the computation is just, is stuff we've done, right?
Yes.
Okay. All right. What's next? Unit tangent vector. I guess we could go through this. This is 3-dimensional, right? 3-dimensional vector function. But look at what it's asking for. Find the vector equation of the line that is tangent at this particular point. Okay, so this is there's a little bit of complication in here. Here's what we want. We have some curve being drawn, right? By the vector function, whatever is happening, it's 3-dimensional. We want to go to a specific point, and we want to come up with the line. We want the vector equation of that line, don't we? Remember, vector equation looks like that. Now, I can't use r of t, because I'm already using r of t for this, right? So why don't we call it, I don't know, What do you want?
Z.
Z of t? Z? How about D? Okay, D of t. I don't care. All right, we'll call it D of t instead of R of t. And we're going to try and draw the line that's going to hit our curve in three-dimensional space, tangent, right, to our curve, and draw the whole line. So if we're going to use this, then we also need to know d naught plus tv, right? That's what we need whenever we want to draw a line in three-dimensional space. We were using r naught, weren't we? R naught plus tv, but because I'm calling it d, I'm going to call it d naught. Does this make sense?
Yes, sir.
Okay, so do you know what either of these are? Do you know what d naught is?
Yes.
What?
It is the vector 0, 1, 5, 0.
Yeah, this point is where we're going to be on the curve, right? So we want to go to that point on the curve and then draw the tangent line. So that point needs to be on our tangent line. So we may as well use that as our d naught. Okay, so I'll put that over here. D naught is that point converted to a vector. Now all we need is the direction vector for the line. And the direction vector for our line should be parallel to what? The tangent vector of the curve, right? So we just need to compute the tangent vector of this, right? The vector function, take its derivative, and then figure out what the vector is at exactly this point. Okay, so let's do the derivative. What is r prime of t here? Hopefully it's a clean derivative. Negative 2 sine t, cosine t, 1. Okay. Now, this is the part that I guess is a little tricky, because we actually need to plug in t to get the exact vector, don't we? Don't we need to plug in t to get the exact vector? This gives us just a general answer. We need to see where are we, right? Where are we on the curve? I know I'm here, right?
Yes.
But that doesn't give me t. That just tells me where I am. So how am I going to get t? How am I going to figure out what t to use here?
You figure out which value of t, and when plugged in the vector r of t will give you the point. Three values.
Yeah, so this curve right here, right, is going to somehow take me to that point. So I need to figure out what t value I would need to plug in here, here, and here. Same t value for all three components that would spit me out right here. And it's kind of obvious, isn't it?
It tells you it's pi over 2.
It's pi over 2 because, look, t has to be this, right? So pi over 2 here, what's sine of pi over 2? 1, and then cosine of pi over 2 is 0. So it looks like this is happening. This right here is actually r of pi over 2, which means that t is pi over 2, which means that's what we can plug in here to figure out the actual tangent vector. That makes sense? You have to kind of extract what t is from the point to be able to use it here to be able to get to this. Questions? So what is r prime of pi over 2? So sine of pi over 2 is 1, right? And then, so negative 2 there. 0, 1. Are we happy with that? All right, and this is the vector that is tangent to our curve at that point, right? That's what it is. And since this vector is tangent to our curve, it qualifies or it satisfies what we need for the direction vector of the line. We just use that vector as v, and we have the direction of the line. So I think we're there, right? The v that we're going to use over there is that vector. And so we can come up with a final vector equation for our line. D of t equals r naught, or sorry, I said r naught, d naught, 0, 1 pi over 2, plus t times v, but v is negative 2, 0, 1. And then I put those together, right? I can put them together all into a nice condensed form. So what's it going to be?
First term is negative 2t.
Negative 2t,
I think the second term is just 1.
just 1. Okay.
Pi over 2 minus
Pi over 2,
t plus
and then plus t. Okay. And then that's the standard form for the vector equation of the line. You could, of course, put it into parametric form or symmetric form, but this is the one that I like to use most of the time. So that is it. If I graph this, if I start, letting t go, I should draw a line that is tangent to my curve in three-dimensional space at that point. And now let's see if we did it. I'm going to leave the vector equation of the line up there. So here's my curve. See what happens as time goes here. So here we go with time. We're going to start drawing the curve. See, I've got my red tangent there. And I need to go to pi over 2. So pi over 2. Yeah. There we go. That's the tangent vector, which I think we did get negative 2, 0, 1, right? And if I draw the line, it didn't come out too good, but you see the little dotted line there? But this is in three-dimensional space. We have found the vector equation of that line. Now, to confirm it, let me go up to my code here to see what I did to graph that line. Where's the dotted line? There it is, right here. Oh, shoot. What in the world did I do? Oh, you know what? This is not going to work because I did my code arbitrarily. So my dotted line is going to move with the tangent vector, so it's not going to look. I was hoping that it would just look like this, and it would verify. But it's dynamic. It's moving with the curve, so it's more of a function still. Sorry. All right, we happy? Yeah. Okay. Now, what about the second derivative? Well, we did second derivatives back in Cal 1, right? First derivative told you the slope of the tangent line. The second derivative had to do with what? Concavity, concave up, concave down, right? Well, when you have vector functions, you can still take second derivatives, right? Just take the derivative of the derivative. But it has a kind of a different meaning here, all right? A vector function r of t given on some interval I is called smooth if, first of all, the first derivative is continuous and exists on I. So let's say that we're looking at some vector curve, right? Some function. And we define it, let's say, on t goes from like 0 to 2, right? So we have a closed interval, and we're just drawing a piece of some curve. Then we will say that that curve is smooth if the derivative is continuous. So when I take the derivative, everything is still very nice. There's no division by 0, no square roots of negatives. Everything's nice. And if what did I say here? And if the derivative does not equal 0, except at possibly the endpoints. Okay, so we're defining something here. Now this is a little confusing because I was just talking about second derivatives, right? This definition does not have anything to do with second derivatives. So just real quick, we're going to talk about smooth. So smooth functions have nice derivatives on the interval, and the derivative is not 0 except at endpoints. Now, think about this in Cal 1. If I graphed this function x squared, right? This would look like this, right? And if I take the derivative of this, we get 2x. And that's well defined, isn't it? I mean, this is nice. There's no division by 0. Everything's beautiful with this thing. Is this ever 0? Is this derivative ever 0? At 0, right? So we do have a slope of a tangent line here, right? Like this. But would you agree that the original function is smooth? Like if we were going to use the word smooth, this x squared would qualify as smooth. With vector functions, to be smooth, You need the derivative to exist. So you need this derivative to be nice. But you also cannot have the derivative be 0. If the derivative is 0, you have a problem, except at the endpoint. So there's something about the derivative being 0 with vector functions that somehow destroys the smoothness. Let's see. I think we need to like visually see this, all right?
That's not smooth.
This is, but that's not a vector function.
Oh.
Okay, that's what I'm saying, is that back in Cal 1, we would look at that parabola as being smooth, right? But now when we have something like that, that wouldn't be. So here's an example. It's two-dimensional. All right, let's talk about the derivative of this. What is the derivative of this function? Okay, so the first part's going to be a little chain rule, right? 2 comes out, cosine, then derivative cosine is negative sine, so something like negative 2 cosine t sine t. And yeah, there's a formula. You could convert that over. That's like negative sine 2t. Who cares? That's pre-cal stuff. We don't care. That's the derivative of the first component function. How about the second component function? 4t cubed, right? All right. So let's take a look at this. Is this well defined? Like, are you ever going to get division by 0 or roots of negative numbers? No, right? You're never going to get anything bad there, are you? Right? Agreed? Like, you give me any t, I'm going to be able to plug it in. I'm not going to have a problem. But is that derivative ever 0? And shoot, did I put 0 vector here? Hold on. This should be 0 vector. Let me see here. I'm trying to remember my shortcuts here. Yeah. There we go. Okay. Everyone please correct that. Because the derivative of a vector function is a vector, right? So we say that the derivative of the vector function can never be the 0 vector. So let's take a look now back at this. Glad I caught that. I better save this document. All right, now, can this ever be the 0 vector? Is there a t that I can plug in that's going to make this thing 0, 0? 0, right? So what's r prime of 0? We get sine of 0, 0, right? So you get 0 there and then 0 there. That's the only point, right? Any other t would be okay. I mean, you could plug in like anything that makes sine 0, right, would work, but it wouldn't 0 this one out. Okay, so this 0, t equals 0, is the only place where we seem to have a problem. This vector function would not be smooth. Let's take a look at the picture of what's happening here. There it is. That's the vector function. And you can see there, let me see if I can start drawing it. Let me back t up. Right now t is a negative number. Okay? So what happens here? We start coming up. Everything's smooth, right? Look at the tangent vector. Red, the red one. Everything's great. And then what happens when we get to 0? Right? I think there, right? We get the 0 vector. So it was like, and then it smushed down to the 0 vector. And then as soon as I go past 0, see it? Look at the direction of the vector. See, it's pointed to the left. See that? And then when I come back, where's it point? To the right and then to the left. And that's kind of like, I don't know, almost like a cusp was in Cal 1, a corner. So, and you can just tell by the graph, I mean, that's not smooth. We have like a cuspy thing happening there. So with vector functions, we have this idea of smoothness, but we have to be careful with this derivative being 0. Okay? All right, rules, differentiation rules. There's a lot here. Let's try and run through these as quick as possible. This is the analogy to when you were taught all the differentiation rules in Cal 1. Like, If you have two functions added together, you could differentiate them separately, right? That's what this says. We have two vector functions. We want to differentiate them. We can just separate them and do them individually. Great. That's exactly what we would expect, what we would hope for, right? Subtraction, subtraction. I didn't put it there for some reason. If we have a constant times a vector function, we want to take the derivative. Constant can come out, come along for the ride just like it did in Cal 1. Now, product rule. This is a little bit confusing, all right? This right here is a little confusing. Remember the product rule, right? You have like two functions being multiplied, derivative of the first one times the second one plus derivative of the second one times the first one, right? Something like that. But notice, look at these two functions here. Are they both vector functions? No. F of t out front is a scalar function. So maybe that's like, let me give you an example of what I'm talking about. Let's say I take t squared times cosine t sine t. This is a vector function, right? Times a scalar function. That's what this is saying. Scalar function times a vector function. If you want to take the derivative of this, you can basically do a product rule on this. You do derivative of this, right? Which would be? So if I say take derivative of this with respect to t, it would be 2t cosine t sine t plus, right? Plus now the scalar function, t squared, times the derivative of the vector function, which would have been negative sine t cosine t. All right? Does that make sense? Okay, so that product rule carries over into scalar times vector function. All right? It also carries over to dot products. So if you take the dot product of two vector functions and take their derivative, you can do product rule, but instead of it being derivative of the first times the second, it's derivative of the first dot the second, plus derivative of the second one dot the first one. You'll see, so we're just using dot instead of multiplication. Yeah? Yes. And then it works the same way with the cross product. If you take two vector functions and do their cross product, take the derivative, you can do it this way. You can just do derivative cross v, right? And then derivative v cross u. Everything should look very much like it did in Cal 1 here. It's just that we have we actually have three different types of multiplication in three-dimensional space and in vectors now. We have scalar multiplication, dot product, cross product. So we have to make sure that the product rule carries over for all of those, and thank goodness for us it does. And the last one is composition. This is chain rule. Vector function with a scalar inside, you do basically like you did in all chain rule, you do derivative of the outside function and then times the derivative of the inside function. All right. Take a look at that function. Two-dimensional, right? Vector function. What does that draw? What does that draw? Cosine t sine t. What does that draw? Unit circle. It's two-dimensional. If it had a z component, it might draw a spiral or something, but this is two-dimensional, so all it's going to draw is the unit circle. Okay, because there's a 1 in front of here, 1 in front of that. If there was a 2 and a 2, it'd draw a circle radius 2. So we want to show that if you draw a circle, the unit circle, then r of t, that vector function, is always orthogonal to its own derivative. And I think it would make sense if you just think about it. If you draw a circle, right, using a vector function, and you look at the tangent vector should be like that, right? And the vector that gets you to that point should be like this. So this is r of t. That goes from here to here, right? And then this is r prime of t. Right? So visually, it makes sense that these should be orthogonal. But what is it that I really have to do then?
Show that the dot product of the two is always zero.
Must show that r of t dotted with r prime of t is 0, because that's how we check it to see if two vectors are orthogonal, right? You dot them. And I think this will be easy to show. So we take r of t, which is cosine t, sine t, and we dot it with the derivative of that. And the derivative of that is negative sine t cosine t. And dot products are the easiest ones to do, right? So what do you get when you do this times this? Negative sine t cosine t. And then plus, and now sine t times cosine t. And they cancel, and you get 0. And that would have held for any t. So dotting the derivative with its own, dotting the vector function with its own derivative means that you get 0, which means that these are always orthogonal vectors. I have the graph. I mean, that's just to show you what I just said, right? No matter, as we draw the circle, our tangent vector, r prime of t, is always orthogonal to r of t. Questions? This one's a little harder. Show that if the magnitude of r of t is c, what does c mean here? A constant. And we're going to assume c is a positive constant here. So show that if r of t, the magnitude of it, is a constant, then r of t is orthogonal to r prime of t for all t. Notice I'm not giving you a specific function, am I? Like in the previous example, I gave you like cosine t, sine t, and we were able to check it just by computing it. But here I'm not giving you that, am I? This is a little harder. So let's first of all try and figure out what this means. This means that as you draw the function r of t, the distance from the origin to the curve is always constant, right? So if you're in two-dimensional space, what do you have to be drawing then? A circle. If you're in does that make sense? If let's say I plug in some value t and it takes me there to that point, right? Then that distance is c, right? And this is saying that for all t, I have to stay that far away. Then as I draw this thing, I have to be on a circle, right? Because I have to maintain that distance from the origin. That's in two-dimensional space. But what about in three-dimensional space? You have to be on a sphere. Now, imagine like a bug crawling around on a ball, right? As long as he's on the ball, he's always maintaining a distance of c from the origin, right? But the path along the ball can be anything, right? So there's a ball. Let's say the radius of this ball is c, right? Then if you draw me any path on the ball, I think I came off the ball there. Any path, right? As long as I stay on the ball, go around that other side, whatever. As long as I stay on the ball, am I not maintaining a magnitude of c from the origin? And I have to show now that in either case, that as I draw it, I always have to stay orthogonal to my tangent vector. So this is kind of difficult to do, all right? Understand the kind of the geometry of this? Question?
Is this the question we just did?
It is, but in the previous problem, I gave us the specific function, right? What I've tried to just convince you of with the picture I just drew up there with the sphere is that there's an infinite number of paths along a ball, so I can't take one specific example. I have to show that this holds in general. In fact, we've only dealt with vector functions in two-dimensional space and three-dimensional space, right? Right? But this extends into 4, 5, 6, 7, as many dimensions as you want. As long as the vector that you draw has a length that is maintaining constant, then your vector that draws your curve is always tangent or orthogonal to your tangent vector. Now, after you get past 3D, you can't visualize it anymore, so it's hard to wrap your head around. That's why we're not messing with 4D right now. We're just messing with 3D, all right? How in the world do you show this? How in the world do you show this? Okay, well, let me try, all right? What do we want to show? We want to show that R of t dotted with R prime of t equals 0. Do you agree that's what we want to show? Right? And all we know is what? What's the only thing we know? The magnitude of R of t is a constant, right? This is what we're given. And we have to show that. Well, how in the world am I supposed to show that these things dot, right? Like this would dot if I don't even know what R is. How can I ever talk about its derivative, right? Like, I don't know what the derivative of R is because I don't even know what R is, right? Yes?
Perhaps you could define.
What if we just wrote it like R1, R2, I mean, that's all we can do, right? Is just put it in vector form.
Like just make up some arbitrary.
Would we have to use values, or if we're making a rule, could we just say like RT equals the vector R1, R2, right? Something like that, and then from there.
I could do like R1 of t, R2 of t, R3 of t. I could do that because remember, these are functions of t. They're not numbers, right? We could do that. Yes?
But if the derivative is always going to be parallel.
But we don't know it is. Orthogonal.
Oh,
We have to show it is. We don't know it's always going to be orthogonal.
okay.
So all we're given is this. All I'm telling you is that the distance from any point on your curve to the origin is always maintaining a distance of c. And from that, we have to conclude that that means that that dot product is always 0. This is a bit troubling, this problem right here, okay? It's a bit troubling. So we might be able to get something with this, all right? We might. Maybe we'll revisit that if we can't get it another way. It's not a bad idea. Just bear with me, okay? Just bear with me here. What is that?
The magnitude of.
You got it?
The magnitude of RT squared.
Okay, where are you getting that from?
Is in our notes.
Yeah, it's in our notes. Dot product section.
Wait, wouldn't this be magnitude of RT, not RT squared?
Let me see here. I'm going to bring it up here. Dot, nope. Cross product, 10.3. Go to 10.3 notes. Where am I? I'm losing it. There you go.
It's in properties.
Yeah, it's in the properties of the notes for 10.3. Oh, I passed it up. Come on. There we go. There it is. First property of dot products. Any vector dotted with itself is equal to the magnitude of the vector squared, right? Agreed? So that is legitimate for me to write this down, isn't it? And what would be the magnitude of the vector squared?
C squared.
C squared. Okay, so is everything here like legitimate? All I'm starting with is this, and then I'm realizing that this is true. Okay, now the amazing part. Yes?
Sorry, no.
Go for it if you got it.
So we're going to differentiate that, and that's going to.
If we okay, so if I differentiate this, I have to use the product rule, right?
Yeah.
For dot products?
Yeah.
Because look, what we're interested in has r with a derivative, doesn't it? And so how can we make this thing have derivatives appear? Take the derivative, right? So if I take the derivative of this right now with respect to t, and then this side take the derivative with respect to t, well, the right side's nice, because that's a constant, right? C squared is a constant. And what's the derivative of a constant? Always. Zero. Now, what's the derivative of two vector functions being dotted? Well, it's the product rule, right? It's the derivative of this dotted with this plus the derivative of this dotted with that. So let me write that down. It's the derivative of r dotted with r of t, right? Plus the derivative of r again dotted with r. Do y'all see that? And remember, dot products, you can switch the order, can't you? Oh, well, I don't need to here, do I? But it wouldn't matter if these were backwards because I can switch it back. Aren't these identical? These are identical, aren't they?
Yeah.
So like, we have two of those. So I'm saying that two of these r prime of t dotted with r of t's equals 0. And then last step, divide both sides by 2. Yeah. Divide both sides by 2 and you're there. You've shown it. That's kind of crazy, right? I wouldn't have expected anybody to go from here to this step. I mean, maybe you'd stumble upon it given enough time, but now you see how you can attack this. Do y'all see it or not? Pretty nice little move there, right? So we've shown that as long as the magnitude of the vector function is constant, that we can take just that simple information and from that determine that the dot product of r and its own derivative have to be 0. And thus, it's orthogonal to its own derivative all the time. I remember the first time I saw that, I was like, what? 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 And for those of you who are math majors, or interested in math majors, that's the type of stuff that math majors have to do. They have to take something like that and they have to figure out a way to get to that result, you know, and it's not always just a natural process. You have to try something, see if it works, try something else. Okay, some applications of derivatives of vector functions. All right, this can get really long and drawn out, so I'm not going to go through these notes like verbatim, all right? What I want you to take from this is that I'm about to draw you two different vector functions. One of them I'm calling R1, the other one R2. The first one is defined t squared, and the other one's defined t squared t to the fourth. All right? And I'm about to draw them. They're both two-dimensional. So we're skipping that. Here they are. Here's R1. Here's R2. And I want you to notice something. They draw the same curve. Don't they? They draw the exact same curve. Would you agree? But here's the thing that's different. If I press play here, watch these dots. See that? This curve gets drawn faster than that curve, doesn't it? This gets drawn faster than that one. Now what I'd like to do, I'm going to slow it down a little bit. I don't know why it's flashing. That's kind of annoying. Okay, so now what I'd like to do is show you their derivatives also. And pay attention to the derivative, the tangent vectors. Do you see the difference? They're pointed in the same direction, like when they get to the same point. Like this one right here, right, is very long, yes? Now if I wait till this one gets to that point, it's going to be the same direction, but it's not as long, is it? So the direction of the tangent vectors are all the same at corresponding points. But it's the length that's different. And that's where the whole idea of the speed comes from. So this vector function is drawn faster, and the tangent vectors are showing you that. Now I can show you a comparison. Yeah, let me get that one out of there. Yeah. God, I wish I didn't have all that crap in there. But what I've done is I've shown here, the black one is R1, and the purple one is at the same point over here. So you can see that the purple one over there is longer, right? So it's at that point, it's moving faster on that curve than it is on this curve. So even though you have two vector functions that draw the exact same curve, they're drawn at a different rate. And therefore, the derivatives should tell you that somehow. All right? And that's what this note is about. If r of t is a vector function which represents the path of a particle or an object through space, then we call it a position function. So if the r of t is telling you where something is, we call it a position function. Then v of t, which is the derivative of r of t, is called the velocity function. And it is actually a function, right? The derivative of r is a vector function, and that's called the velocity function. Does this seem familiar? Right? In Cal 1, if you had a position function, s of t is what we usually used. Then v of t was the derivative of that. And then the second derivative was acceleration. Okay, it's same sort of thing here, but there's a major difference. When we take the derivative of r of t, we get a vector function, which is our velocity function. Now, if you take the magnitude of that vector, the length of this vector, how long it is, then that's the speed of the particle. So back in Cal 1, when we talk about velocity, we pretty much say velocity and speed are pretty much the same thing, because in Cal 1, we always assume something's moving in a straight line. So we don't have the idea of a vector in Cal 1. But here in Cal 2 and in physics, I'm sure if you've taken physics, you understand that there is a difference between velocity and speed. Velocity is usually a vector which represents, you're going to have a magnitude, direction. I couldn't get out, a direction, right? It's going to have a direction, and it's going to have some sort of length to it. But it's a vector, right? 2 or 3 components. It's a vector. That's velocity. Speed is the length of that vector. That makes sense? Questions? Now, your second derivative is your acceleration function. But guess what? Acceleration is a vector still. So with vector functions in 3-dimensional space, we have first derivative is a vector, second derivative is a vector. Lengths of those things are speed and well, there's really not a name for the length of the acceleration vector. The length of the velocity vector is called speed, but the length of the acceleration vector is not defined unless we're straight line motion. If we're straight line motion, then the acceleration is just a number, and that's just the length of the vector. All right, the larger the magnitude of the magnitude of the derivative, the faster the particle is moving at that point in time. Look at page 589. What? Let me look at this real quick. I don't remember what. Oh, where's my book? I just want to make sure I'm not missing something here that I want to show here. Examples 2 for 2, 4, 8, 12. Yeah, you know what? This is stuff we've already talked about. The first problem has to do with finding the domain of a vector function. Maybe we should just do one of those. I don't know. What do you think? Should we do a domain one? Well, we don't have the time, but you know what? Let's not, because domain is just let me put it this way. When you have a vector function that has multiple component functions, right? Individual component functions. We already saw it. Take the limit, you do each one, right? You take derivative, you do each one. If you're looking for the domain of a vector function, you have to look at each component function and look at its domain for each one. And then what you do is you find what all of them have in common. And that would be the domain of the vector function. So domains is something you should be familiar with. Everything else here is like finding a limit or or taking a derivative. So I think we're ready to proceed. All right. Y'all doing all right? Okay. Remember, I'm just the messenger. 10.8. Arc length and curvature. Well, if we're going to be drawing curves in 2 or 3 dimensional space, then we may as well be able to measure how long they are, right? Why not? And maybe I'll remind you, yeah, I will remind you, back in Cal 2, that when you had, you know, x, y, and then you had some function of x here in between a and b, that if you wanted to know the length of that curve, like take it off the piece of paper and straighten it out and measure it, that was referred to as arc length, was going to be integral a to b square root of 1 plus the derivative of the function, that quantity squared dx. That was the, does that formula look familiar? That's from Cal 2. Okay? It looks familiar, right? Okay. All right, we won't go into where the formula comes from other than to say it has to do with like setting up a little triangle and doing a little Pythagorean identity and taking a limit and anyway, okay. So, we want to be able to do the same thing, but we want to be able to do the same thing for a curve that's in 3-dimensional space or 2-dimensional space. Either way. So, arc length, the definition. I need to make this a little bit smaller. Suppose you have a 2-dimensional vector function. Okay, as t, now t is going to be only going between 2 values, a and b. So we do have to just draw a segment of the curve. And we also have to make sure that we only traverse the curve once. Let me give you a quick example. Let's say we had the vector function r of t equals cosine t sine t. We already know that draws the unit circle, right? If I let t go between 0 and pi over, 2 pi, sorry, that's going to draw the circle one time, right? Then we can use this formula. But if it goes to 4 pi, we're drawing the circle twice, once on top of itself, right? And there, in that case, this wouldn't apply because we are traversing the path, the curve twice over itself. So what we'd have to do is we'd have to figure out what it takes to traverse once, and then like we'd have to determine, ah, wait, we just go to 2 pi, and that'll be our arc length. Does that make sense? So long as we are traversing the curve only one time, then here's the formula. It's a freaking beautiful formula. Look at it. Integral from a to b. Now a to b are restrictions on what? A and b are restrictions on t. So we no longer have like the x-axis a and b. T is a clock in the background, okay? And then what we're doing is we are taking the, what? Magnitude of the tangent vector, right? That's what we're doing. We're taking the magnitude of the tangent vector and then multiplying it by this little differential dt. Now, we know that the magnitude of the derivative would be this. Now, do y'all see where that comes from? It's up further. R of t is 2 components, f of t, g of t, right? So if we say take the derivative of this, it's just going to be f prime g prime, right? Right? And then if I say take the magnitude of that, you're going to do the square root of each of those squared, which is that. Okay? So that's just the magnitude of the derivative, and then dt. We can look at this. I know in my Cal 2 class, I stress to my students that the integral sign means that we're adding up an infinite number of little tiny things. And so what we're doing is we're adding up, we're taking like an infinite sum of infinitely small tangent vectors. And do I have a picture? I don't know if I have a picture. I don't. but I can kind of illustrate. If we want to find the arc